Hi students, welcome back to Wisdom Academy YouTube channel. We are learning magnetic effects of electric current. In the previous video, you have learnt about the applications of Biot-Savart law. So I said you Biot-Savart law is for finding the magnetic field due to a current element. And what was that? dB is equal to mu naught by 4 pi I dl sin theta by r square. Also I told you in the applications of Biot-Savart law, by using Biot-Savart law, we can find the magnetic field due to a straight current carrying conductor. We can also find the magnetic field due to a circular current carrying loop. For a straight current carrying conductor, if the point is taken to be at the center of the infinitely long wire, then the magnetic field value will be mu naught I by 2 pi r. And the magnetic field due to a circular current carrying conductor at its center will be mu naught I by 2 r. We also found for the axial point, there was a big equation there, and all these things are very important. Today we are going to continue from there and we will solve few numericals based upon that, and then we will enter into the next topic. So what is the first numerical? The radius of the first orbit of hydrogen atom is 0.5 Ampere, Armstrong. So if suppose it's a hydrogen atom, then they are saying the electron is taking around and the radius of the first orbit, this orbit is given as 0.5 Armstrong. This is the radius of the hydrogen atom. The electron moves in the orbit with an uniform speed of 2.2 10 power 6 meter per second. So this electron which is moving, they have given the velocity of that electron as 2.2 10 to the power 6 meter per second. What is the magnetic field produced at the center of the nucleus due to the motion of this charge? So they are asking what is the magnetic field at the center due to this movement of electron. We know very well that magnetic field at the center, it is like a magnetic field due to a circular loop at its center. So we know the formula B is equal to mu naught I by 2 r. This is the formula of magnetic field due to a circular current carrying conductor. Now in this case, r is known to us, mu naught value we know, I is what we want to find. So for finding the current, we know the current is equal to charge per unit time. Now charge we know for an electron, time we want to know that how much time it will take to complete one round. So to find a time, we know that time is equal to displacement of velocity. What is displacement? 2 pi r it will be. So it will be 2 into pi into r by velocity. What is the velocity? Velocity is this, that is 2.2 10 to the power 6. So this will give me the time period. This much seconds will be the time period of this electron which is taking this turn. So when you solve this, 2 into 22 by 7 into r is 0.5 into 10 to the power minus 10 and divided by, here we have 2.2 into 10 to the power 6. This becomes 10 times and this goes above, makes it 10 to the power minus 16. So it will become almost 1. So I will write 1 by 7 into this will be 1 and the 10 will go there 10 to the power minus 15. So 1 by 7 10 to the power minus 15 seconds is the time taken to complete that revolution. Now time is known, Q is known, so I will be equal to what is charge on one electron? It is 1.6 10 to the power minus 19 divided by this, that is 1 by 7, 7 will go above at 10 to the power minus 15. Well, this gets cancelled, it becomes 10 to the power minus 4. So I get somewhere near to 1.6 into 7 into 10 to the power minus 4 ampere as the current which is coming. Now what will be the magnetic field? Magnetic field will be equal to mu naught. What is the value of mu naught? We know that mu naught by 4 pi is equal to how much? Mu naught by 4 pi is 10 to the power minus 7. So we can take mu naught value as 10 to the power minus 7 into 4 pi. So it will be 10 to the power minus 7 into 4 pi into current is 1.6 into 7 into 10 to the power minus 4 divided by 2 into r is 0.5 into 10 to the power minus 10. When you solve this equation, this much Tesla will be the magnetic field produced due to this electron moving around the nucleus. This kind of questions are also asked frequently, where they ask you to find the magnetic field at this point O in such a way that a wire is bent in this form. So the wire is bent in the way that it has 3 sections like this, and each section is r distance away, like this is r, this will be 2r and this will be 3r from this point O, and they will ask you to find the magnetic field at this point O. So this question is a bit complicated, where you have to think properly in how to find the answer. So if I join all this point, it becomes like a sector. So in a circle, from the center if you see, there is some angle theta which is being considered here, right? So now what I am trying to say you, please understand that we know that magnetic field due to a circular current carrying conductor B is mu naught I by 2R. But this B is for the complete circle. So this B is for 2 pi. So I will write for 2 pi degrees or 2 pi angle, B is mu naught I by 2R. So for one angle, B will be equal to mu naught I by 2R into 2 pi, and for theta angle, B will be equal to mu naught I by 4 pi R into theta. This will be the magnetic field due to the theta. Now if you see which are the current elements and which point you have to find the magnetic field because of what part. So the current flows from here. So it goes like this, then it goes again like this, again it goes like this, again goes like this, goes like this, and again finally it goes like this. But there are three elements I, and I, which are in this direction, and if you see the direction of current and the DL is in the same direction. The current is like this, even DL is like this. So when I and DL are in the same direction and theta between them becomes 0, then what will be? B is I dl sin theta. So even B will become equal to 0, isn't it? So the magnetic field due to these three portions, this straight line, and this straight line will be 0. Now what remains is only this curved portion, and this curved portion. Now finding the value of magnetic field to these three portions, these three behaves as a sector of a radius r, a radius 2r and radius 3r. Let us try to find. Let me name it as B due to the first wire, B due to the second part and due to the third part. So I will write B due to the first part will become equal to mu naught, I have got the formula here, I by 4 pi r into theta. What will be B due to second part? Mu naught I by 4 pi, now it has become 2r, r plus r 2r, so I will write here 2r into theta. And what will be B3? B3 will be mu naught I by 4 pi into 3r into theta. Now one thing you have to consider here, see the direction of this, if we are taking it as positive, then this will be positive and this will become negative, isn't it? So the magnetic field produced due to this wire, if you are taking it as positive, then this will be taken as negative because the direction of current is opposite, or vice versa, if you take this as negative, this will be taken as positive. So I am taking this 1 and 3 as positive, so this will become negative. Why it becomes negative? Because direction of current is opposite as compared to first and third case. So now to find the net magnetic field, B net will be equal to B1 plus B2 plus B3. That will be equal to mu naught I by 4 pi r into theta minus mu naught I by 8 pi r into theta plus mu naught I theta by 12 pi r. So if I take mu naught I theta by 4 pi r as common, remaining here will be 1 minus remaining here will be 1 by 2 and remaining here will be 1 by 3 plus it will be. So if I take the LCM, mu naught I theta by 4 pi r, the LCM will become 6. It will be 6 minus 3 plus 2. So 6 plus 2 is 8, 8 minus 3 is 5 and it will become mu naught I theta and it is 5 here divided by 24 pi r. This is the value of magnetic field at the point O. Now let us see the next topic, that is Ampere's circuital law. Ampere's circuital law you can relate with Gauss law in electrostatics. So in first chapter you studied about Gauss law, and Gauss law is an alternative form of Coulomb's law. So by using Gauss law you can find the electric field at various conditions. What was Gauss law? It was about total flux enclosed, and we say total flux enclosed by any Gaussian surface is 1 by epsilon naught times the net charge enclosed. Total flux we can find by any particular charge. Same way, by using Ampere's circuital law, we can find magnetic field for any current element. So what it says that the net magnetic field around any closed loop is mu naught times the current passing through that loop. I will repeat once again, the net magnetic field around any closed loop is mu naught times the current passing through that loop. So if I take the line integral B dl, that is equal to mu naught times of I. This is the Ampere's circuital law. Now Ampere's circuital law, for this law, using this law we need a loop, and that loop is called as Amperian loop. Amperian loop. Since it was found by Amperes, it's called as Amperian loop. So how this formula came? Let us try to derive it. We can derive it by for a straight current carrying conductor. So let us assume that there is a straight current carrying conductor carrying I, and I will take any point here. So I told you, if you take any point around its radius, it will have same magnetic field. And how much will it be? I have told that magnetic field around a straight current carrying conductor B will be equal to mu naught I by 2 pi r. So if you take any point here, let this point be x. At this point, what is the direction of magnetic field? It is somewhere tangential. And what is the direction of current element? It is also in the same direction, isn't it? So now, if you take this BDL component, let us try to find out what is that. So integration of B dot dl, that will become equal to integration of B dl cos theta. B dl cos theta. What is theta between them? Theta between dl and B is 0. So this is dl direction, and this is direction of magnetic field. Angle between them is 0. So cos 0 is 1. So I get that is equal to integration of B dl. So integration of B, and what is dl? dl is the length. Length of this loop is a circle. Now this is the Amperian loop I have drawn. So what I have done, the current carrying conductor, I have drawn an Amperian loop out. This is the Amperian loop. So Amperian loop is a closed loop, imaginary loop, which encloses the current. So now if you see, what is the integration of dl? It is 2 pi r. So B into 2 pi r. What is B from here? You can say mu naught I by 2 pi r. So I will get mu naught I by 2 pi r into 2 pi r. These two gets cancelled. So what you get? Mu naught I. What I took? Integration of B dot dl. So from here I can prove that integration of B dot dl is equal to mu naught into I. This is known as Ampere's circuital law. Not only that, we can find the Ampere's circuital law by taking the help of straight current carrying conductor. We can use even the inverse of that. That means by the help of Ampere's circuital law, we can even find the magnetic field to the straight current carrying conductor. If you want to know, it's very simple. Suppose I am taking a straight current carrying conductor and I want to find what is the magnetic field at this point by using the Ampere's circuital law. Then what I will do? I know that Ampere's circuital law says that in line integral of B dl is equal to mu naught I, and we know that B and dl direction are tangent. So the angle between them is 0 degree. So dl direction and B direction are in same. Theta is 0 between them. So line integral of B dl cos 0 is equal to mu naught I. So B line integral of dl will be equal to mu naught I. And what is integration of dl for a circle? It will be 2 pi r. So B 2 pi r is equal to mu naught I. So magnetic field will be equal to mu naught I by 2 pi r. Now isn't it the magnetic field of a straight current carrying conductor? Mu naught I by 2 pi r. So here I have proved the same magnetic field by using Ampere's circuital law. If you see properly, it is just the inverse of what we have learnt in the previous thing. Let us start the next topic now, which is solenoid. So what is solenoid? I think you studied about solenoid also in a 10th standard. Please recall it, you will come to know. It is the arrangement of insulated copper wire wounded together in helical form. If I draw it, it's something like this, where for long solenoid, always the length of the solenoid will be more than its diameter. So always the length of the solenoid should be more than its diameter to be called as long solenoid. Why we go for solenoid first of all? So solenoid, we want to produce magnetic field, a strong magnetic field, we go for a solenoid. But why can't we do it with one turn of wire? So we already saw that if there is a one turn of wire like this and we found the magnetic field around it, you remember the experiment did in our 10th standard where we kept one cardboard in this way and then we sprayed some and fillings on both the parts and connected this with some polarity, and then we got some concentric circles here, some concentric circles here and some parallel lines here. We got something like this. Now these lines which were parallel, what I want to do, basically I want to make the solenoid as a magnet, right? I want to create some magnetic condition. If you take a magnet, then how will the magnetic lines of forces will be? From north towards south. So it goes like this, it goes like this, it goes like this, it goes like this, and it enters south and comes out from north. This is how it is. So I wanted to create artificially this condition. This is the magnetic lines of forces of a permanent magnet. I want to create the same magnetic lines of forces by using some device. So if I take only one turn, then I will get only line which is nearly parallel. Suppose if instead of one turn, if I take two turn, what will happen? Line will become little more parallel. If I take three turn, what will happen? It will become little more parallel. So finally, if I take n number of turns or more number of turns, then I get a uniform parallel line inside, and then I get some circular magnetic fields outside which resembles much with the magnetic lines of forces of a permanent magnet. So if I combine everything together, then I get some field similar to this where I have, like inside we have parallel lines. So same way we have some parallel lines, and on the right and left side we have some concentric circles like this. So I get this kind of condition by using many number of turns, and that is what is called as solenoid. So solenoid is insulated copper wire. When you are wound to make it in the form of a helix, it is called as solenoid. So if I am drawing the magnetic lines of forces, I have drawn it here. It's looking something like that. And one thing I want to tell you that the magnetic fields are very strong inside a solenoid. If I want to draw the magnetic lines of forces here, I will draw it like this. So inside is like this, outside like this. So what happens? The magnetic lines of forces are very strong inside but very weak on this part. So on this part if you take, or this part you will take, they are very weak, and they both, see, the direction of magnetic field at this point and this point will be opposed to each other and they will cancel out each other. So what generally we do for a solenoid, we take the magnetic field at an exterior point to be almost zero, negligible, and magnetic field only if the interior part of the solenoid is considered. Generally that is what we do. Someone may think that suppose there is a solenoid taking current from this direction to this direction like this, coming, going, again coming, inside and going. So it is coming from like this and going like this. What end of the solenoid will act as a north pole and which end will act as a south pole? For that there is something called as Ampere's right hand rule. So Ampere's right hand rule will help you to determine what is the north polarity and what is the south polarity of a solenoid when current is flowing through that. So to understand Ampere's right hand rule, what we should do? We should hold the solenoid in our right hand in such a way that our four fingers are giving the direction of current flow. So suppose current is flowing in this way, it is going like this in a clockwise way, then our thumb will give the direction of north polarity. So suppose it is going in this way, which is like clockwise way. So when the current is going clockwise, then the direction of north will be in this side. I mean for you it will be your right side. And suppose if I am holding in this way your solenoid and the current is going anti-clockwise, then the direction of north pole will be left according to you, it will be left side. So for using Ampere's right hand rule, we have to hold the solenoid in our right hand in such a way that our four fingers are given the direction of flow of current, then thumb gives the direction of north polarity. In this case I have taken the current to flow in what way? I have made to flow in a clockwise way. When the current is flowing in a clockwise way, then this will become the north polarity, this will become the south polarity. So to determine the north and south polarities of a solenoid, we must hold it in our right hand, and then we can find what is the north and what is the south polarity. So after solving a few numericals in today's class, we learnt about Ampere's circuital law, we learnt the proof of that, and we learnt how to reverse it and find the magnetic field due to a straight current carrying conductor by the help of Ampere's circuital law. Then now we have discussed about solenoid, what is it and how the magnetic lines of forces are formed inside a solenoid. In the coming class, I will talk about determining the magnetic field inside a solenoid and also about toroid. Till then, please like the video, share with your friends and subscribe our channel. Thank you very much.